So I want to make sure and acknowledge Jason's song. Jason is one of the people that you'd love to work with. He's bright, intuitive, and he's practical. And so a lot of the work that's gone into this paper and the thought process comes from Jason. So I'll set the context for climate in the way we would like to present it to you today and talk a little bit about tailings dewatering and some key points. So long, cold winters, as we know, hot, dry summers. There is an annual moisture deficit. There's also very much a seasonal moisture deficit. There's a lot more evaporation in the summertime than there is precipitation, which makes it potentially maybe we could take advantage of that in terms of achieving some strength characteristics. How do you dewater? Well, there's decanting, there's evaporation, there's underdrainage, and we're primarily going to talk about today about evaporation. The paper deals with some of those other aspects there. Just wanted to concentrate on evaporation in the interest of times. So, what attributes of the site or the area can we exploit, enhance, or combine to achieve our performance criteria? What are the big stones? What are the big things? That's one of the things that Lee Barber always talks about. What are the big stones that you can take advantage of? And we like to think of this in the respect of, as we move down this triangle, right, there's more and more engineering that we can apply, and we focus in on our dewatering options as we move from the very big stone, which is climate. Climate is something that we just have to take. It's what's there. We can't do anything about it. You may be able to do a little bit about it with respect to snow melt and snowpack by wind fences, or if you have a slope on a south-facing slope, etc. But in essence, climate is climate. That's the big stone. That's the context. That's the thing that we're dealing with, right? As we go through, and we can alter a hydrogeologic setting. I mean, a lot of times when we do our trials, our little cells, right, we take and put it on sand, and then the next lift goes on top of tailings. Well, we've altered the hydrogeologic setting because we've altered the underdrainage conditions, right? And you can think of other ways that you might do that. And then we can spend a lot or a little bit of money altering the materials and manipulating materials, and we can spend a lot or a little bit of money altering and managing the deposition processes. But the idea there is climate is the big one, and that's the one that we have to deal with first, because it's the big stone. And what we're after here is achieving or determining what's the cubic meters of tailings that I can place on a per square meter basis for any given time of the year. So the first step is developing a conceptual model. Right? So here's a conceptual model of a tailing cell where I'm going to try and figure out just how much water I can take away from the system. So I place my tailings, I'm going to have my water balance, right? Standard water balance, changes in storage, water in, water out, precipitation, evaporation. Let's put it into the context of tailings management. Rather than saying changes in storage, I'm going to use changes as solid content as the metric for the example here. You can have all kinds of different metrics, but that's a metric we're going to choose here. And rather than saying groundwater out, I'm actually going to say underdrainage, right? So I can have some precipitation, some runoff in, runoff, groundwater in, some evaporation, and some runoff and some underdrainage. But the idea here is how does my solids content change? And if I'm smart, I can get rid of the run-on and the groundwater in to be able to take advantage of it. I can spend a little money manipulating it, or if I can't, make sure you understand the influence of it. Okay? So I'm taking something from an initial state, and I'm taking something to a final state over time. Let's not worry about the metric here. You can choose whatever one you want to describe these two different states. We're probably going to use in this one maybe solids content or void ratio. Just make sure if you're using solids content, you're understanding your fines content, that you've normalized it. And the idea is how and why does it get there? What are the mechanisms and processes and characteristics that control and influence in that behavior? We're going to talk about underdrainage, consolidation, and evaporation, but primarily we're going to talk about evaporation here, right? So how we get there typically is through some characteristics and characterization and usually some numerical modeling, right? But what Jason's method that he's developed here is to say, let's just actually take a step back here. Do we want to run a numerical model that has all these different processes in it, right? And it essentially starts to run on real time, right? Because it's so complicated, right? And what Jason is putting forth here is, let's use that numerical model, or a semi-analytical model, to allow us to integrate in spatial and temporal variability. Those are the big stones, right? That's what changes and influences things the most, right? So let's utilize these numerical models, evaporation, consolidation, and make sure you have the correct rules in there and the guidelines for guiding your semi-analytical model. But if I use a large climate database and model the influence of my system with respect to that database, now I'm getting the understanding of a temporal scale. And you get a bigger picture evaluation. It allows you to provide simple, concise messages that inform management decision, as opposed to having a big, complex model that you can maybe run 1 or 2 years of data on, as opposed to a longer-term climate database. This is the big stone. So here's some initial conditions, right? Let's just assume what we have here. We got to characterize things properly, et cetera. So Jason is using some numbers from a lot of the monitoring we do up in the oil sands. And we're going to look at evaporative drying. We got some initial conditions. We're going to have evaporative drying over time. And he's going to lose some water here, and how much did happen. But it's not how much it happened. What's the probability of moving from my initial state to my final state, which is what I desire, and what's the probability of removing that water and achieving that final state under the climatic influences up in the oil sands? So let's talk about one of the big ones, the mechanisms, evaporative drying, right? So that's a function, as we know, of vapor pressure, temperature, wind speed, energy that's available for evaporation, right? And then we go, thanks to Ward and all the work that he did over the years, we can think about, we know that if we know the temperature at the surface, or really and truly the vapor pressure at the surface, we can understand the vapor pressure gradient, and I can actually figure out what my actual evaporation rates are. And then we have to worry about, what about that stupid salinity and cracking issue? Well, I'm not going to be able to address salinity today in the interest of time, but I am going to talk to you a little bit about cracking. So this is our conceptual model based on monitoring that we've done up in the field, up in the oil sands, and at other places around the world. We always think that we got these cracks that increases our ability to evaporate, but do they really? In the daytime, right, I've got warmer temperatures outside and cool temperatures in my soil, so that influences the humidity and the vapor pressure condition and the temperature inside my crack. And if I've got cool air in that crack, what happens to cool air? Cool air stays what it is. Warm air rises. Cool air stays what it is. So I'm not getting evaporation from those cracks during the day. But if I go to the evening, I've got a different situation. I've got cool temperature here, warmer temperature in my soil, warmer temperature in my crack, and I set up a convective current. Warm air rises, it takes that moisture up out of that crack, and I'm actually getting actual evaporation from the crack during the evening when I've got my convective current set up. During the day, it's dominated by evaporation from the soil matrix, as according to that equations that we showed you before. So yes, there's an enhancement due to cracking, but it's not what some of us might have been led to believe. And we're taking that extra energy and water away through the wind speed. So we've gone from tailings and evaporation to the evaporative water. Now we got to figure out underdrainage. Not a lot of time to talk about this. But in essence, in our experience, initially the underdrainage is controlled by the underdrainage permeability condition, the hydraulic characteristics of that material, the initial pore water conditions, the permeability, etc. That's very early on. Pretty quickly, you consolidate that material, and it's the consolidation characteristics, the permeability of that tailings material that's going to control your underdrainage condition. So now let's look at that big stone again. So we talked a little bit about some mechanisms. We understand that. We're putting that into our model. I've got precipitation or potential evaporation on a scale from 0 to 140 millimeters on the vertical axis, and January to December on the horizontal axis. And what I'm showing you is precipitation and potential evaporation in red and blue on a long-term climate database for this particular site in the oil sands. It's over 100-year climate database. And it'll slightly change as you go from site to site at different spots in the oil sands, right? But generally this is it. And the bigger picture here is that, boy, there's some energy here that I can take and use. There's some excess energy here I can take and use to do water tailings. But how much can I take of that? What's the probability of allowing me to take advantage of that? And if I was really smart and managed my runoff here and ponding, I maybe actually steal a little bit more energy during these hot months. So this is the probability of exceedance as a function of placement thickness of tailings for different months of the year due to evaporative drawing. So I've got a probability of exceeding of 80% for the month of September. If I put my material out at 10 centimeters thick, I've got an 80% probability of moving from my initial state to the final state that I want to be at. Right? As I have higher evaporative conditions, as I go to May and August and to June and July, my probability of meeting, say, 25 centimeters is about 80% probability as well. Right? And I'm using it. That's what happens potentially on any given year, right? Not on the average. And this allows us to take advantage of all that 100 years of climate database and understand the response of the system to it, not apply an average year. So that's fundamentally different than doing your statistics on climate. I'm doing my statistics on the response of the system to a long-term climate variability, and that's the bigger picture. That's the big stone that we want to be able to capture. Because I want to make decisions based on probability and risk, not on average. Because then I understand where my risk profile is. I can go and put out 30 centimeters of material in September, and I've got a low probability of exceeding that. I'm not saying you shouldn't do it, but understand what risk you're taking. The two key messages here, it's not a question of pass or fail. It's not based on the average. The average doesn't exist. It's what's the probability of me meeting my objective. And do you want to be in a situation and play a risk profile where I've got barely a chance of meeting it? Or do you want to play in the risk profile where I have a high probability of exceeding it? It's up to you. The key to surface water management, remember we talked about trying to take advantage of that little bit of extra energy that might be available? Well, the key to water management for these tailing storage facilities is to understand connectivity, right? We've got these fairly flat surfaces, and they will pond water. Right? So am I on a situation where on the left-hand axis I've got shallow slopes and then maybe steeper slopes on the right-hand side over here. On the left-hand side I'm filling my little holes and crevices and cracks, and I've got my fulcrum, my balance of fill and spill is way more on this side. So basically I'm not getting rid of that water. Any energy that I do have is taking up for evaporating ponded water as opposed to dewatering the tailings. Or can I set up a system and engineer the system and spend a little money and get myself over to the far right over there where I've got more filling happening. And now I've got, or spilling happening, and now I'm actually taking that water off the landform. I'm not wasting my evaporative energy, and I'm actually using it to dewater tailings. So the key points, one key point, don't use a pan evaporation system. It's just a bad way. Just measure the climate and figure out what potential evaporation is. But another more bigger picture thing is first, develop a conceptual water balance. What you see there is a conceptual water balance for one of our clients. Talks about how much underdrainage there is, talks about how much water you're losing from decant initially, talks about what's the evaporation that you can sort of count on as you move forward for different months of the year. And then each and every year, that's based on a bunch of measurements, each and every year, conduct your field monitoring to update that thinking, update that conceptual model, and see, do we know any more? Is there another mechanism or process that we can add into this to be able to learn about and include it in our bigger picture conceptual model? And you can go to the lab too, but make sure in the lab that you ensure spatial and temporal scale are realistic, right? We don't get the kind of cracking that you get in the field and lab because of a spatial scale issue. We don't get the kind of temporal things in the lab because we're trying to evaporate things and apply, rather than say 3 or 4 millimeters per year, 6 millimeters per year to make the lab program move along faster. So the method that we presented, I think it allows you to take advantage and think about the spatial and temporal influences climate. That's the big filter. That's the first filter with which we need to move through, right? And allows us to take the longer climate database rather than having a really big super fancy model that does everything that actually isn't be able to model in real time almost. We've showed you how you can apply this model to evaporation and drainage. Jason's got a lot of other things in his pocket to talk about, you know, thaw consolidation, all the other kinds of things that you might want to talk about. It's transferable. We help the folks down in South Africa, the SLR, help one of their clients using this model. Different rules for evaporation, different evaporative rates, but it's still initial, final, what's the probability of getting there for different thicknesses of material. And it allows for clear and concise information to inform management decisions, because it allows you to have a probabilistic approach rather than designing on the average, because the average doesn't exist. And it's based on the response of the system, not averaging and doing your statistical analysis on climate.